example of a related rates problem. We're going to see one more type of equation that you might encounter along the way. Example 7 says a balloon is rising vertically from the ground at a rate of 3 feet per second. A person is standing 75 feet away from the point on the ground directly below the balloon. Find the rate in feet per second that the distance between the person and the balloon is changing when the balloon is 40 feet above the ground. So we have a balloon going straight up. Going to draw our picture. And it is going straight up at a rate of 3 feet per second. We did not let go of the balloon because we are standing over here 75 meters away. Is that 75 something that's going to change according to this problem? Shoot.
Oh.
Yep. Yep. Yeah, sorry. And I know what the problem looks like, so I'm not thinking it through myself, so I may have said it a little bit quick. Yeah. Yep. A person is standing 75 feet away from that point on the ground directly below. So we got 75 feet here. Is that static or dynamic? That's static, yeah. I mean, it could be. Now, don't keep in mind, if it's a two-part question, like part B could say the guy starts moving or something like that. But it doesn't. So in this part of the problem that we're at, it's static. And we want to know how far the person is from the balloon. So we're actually going to measure a straight line from the person to the balloon. So we're going to draw a diagonal, and we're going to end up with a right triangle there. We will draw that distance to his feet. I could have added extra words in to say that, but in this case, I just say it out loud. So yeah. All righty. So we've got everything in the problem. I didn't mark the number 40. Is 40 static or dynamic? Dynamic, right? Because that balloon is going up, and we want to know how far away is that balloon getting from the guy when it's 40 feet above the ground. Okay, so we don't have an equation, but based on that picture, Pythagorean theorem, right? So we will label these three sides A, B, and C. We can note that we're going to do A squared plus B squared equals C squared. We will note that A equals, what does A equal? 40. B equals 75. This is static, or sorry, backwards. We said these already. A is dynamic, but B is static, which is why it's labeled in the picture. Can we figure that C squared out? Yeah, right at that moment in time, we could figure out how far the person is from the balloon. So we'd have to use the Pythagorean theorem for that. So we end up with 1640 squared plus 75 squared is our C squared. As soon as calculations get calculation-y in these, feel free to use your calculators. I don't know what 75 squared is off the top of my head, although it is 625 times 9, which I probably could figure out. Someone save me from myself and type that in the calculator before I do 625 times 9 in my head. 5,400 plus 9 times 25. 5625?
Yeah.
What's that?
75.
Yeah. You didn't save me from myself. I got the answer before you. So we got C squared is 5625. Please don't make me do the square root of that in my head and type it in your calculator.
Wait, no, hold on.
Oh. Oh, you're right. Sorry. Yes. Because, yeah, my bad. I didn't do that. That's where that number came from. So 7225? Got it. Cool. And C equals 85. Yep. That must be, there is a right triangle relationship there, but it's multiplied by something. So anyway, so yeah, that's where we're at. So we know that C equals 85. So we have all of our measurements there. We want to find the rate in feet per second that the distance between the person and the balloon is changing. So what do we want to find? dc dt, right? Yeah, we want to find dc dt. Okay, So we'll write that down as our last thing. I think that's an important problem-solving step because it can lead you certain places. So dCdt equals question mark. Okay, so that's our setup. We're ready to go. Remember, static variables get plugged in. So we're not working with a squared plus b squared equals c squared. We are working with a squared plus, what was that number? 60, what, 25? What was 75 squared?
Oh, 5.
56. That's where it was. That's why I couldn't get it. I knew it was a 6, but I had it in the wrong spot in my brain. Boom. Equals c squared. So static variables go in. The reason I can do that is because dB dt, the thing that I filled in, what's the rate of the distance between that point on the ground and the person changing at? 0. So that's why static variables can go in. So we end up with 2a dA dt equals 2c dC dt. Then we really have a simple algebra equation to solve here. So we've got 2 times a is 40, so we've got 80, and dA dt is positive 3 because the balloon is going up, which means that line is getting longer, equals 2 times 85, so say 170, dC dt, which is the thing we're trying to figure out. So doing some quick math, it sure feels like 240 over 170. Yeah. Which can simplify to 24/17. So 24/17, our units are feet, and it's per second. Cool. Ready for the fun one? Come on. All right. Letter B says, at what rate is the angle of elevation from the person to the balloon? Those words mean we're looking at this angle right here. Changing when the balloon is 40 feet above the ground. So we're keeping that same time and place. I need an equation with theta in it. Definitely some trig. We could actually do any of the three because we have all of A and B and C. It's usually good form to stick with numbers when possible that you haven't figured out. So we know that A is 40. We know that B is 75. We haven't figured out either of those numbers. So which trig function would I correctly use if I wanted to look at sides A and B? Tangent. Opposite over adjacent, right? So I'm going to go with tangent of theta. Good form. There's multiple ways to do the problem. Somebody who's has a lot of experience doing the problem will do it this way. That's what good form is. That's what I mean by good form in this case. So you could have used sine. You'd write sine of theta equals A over C. Yeah, and they should all work because one of them's always changing and one of them, the worst one to do would be to do, actually sine would be the hard one to do because what we're going to do next, B is a static variable, so we're going to write tangent of theta equals A over 75. We only have two variables, theta and A. If you did sine, you'd get the right answer, but you'd write sine of theta equals A over C. And the problem is A and C are both dynamic. So at the point where we go to differentiate, we are going to be having to use the quotient rule. So yeah, sine would be ugly. So maybe the best thing to say there would be that make sure you include a static variable in there. So B's kind of locked in because it's static, and why not use A because that's the one they gave you. All right. So we may need to we'll have to take our derivative and find out what's going on here. There's a couple different ways to do this problem. We could take the derivative right now as is. That's probably the easiest. We're probably going to need the value for theta at this specific time in order to do that. Yeah, we're definitely going to need to do that. So if tan theta is A over B, in this case, right now at this moment, that is 40 over 75. How do I figure out theta? Yeah, inverse. Yep, that's the whole point of inverse. It tells you the angle that has that tangent. Like I know my angle and I know my angle's tangent. I should say I don't know my angle, but I do know its tangent. That's what our inverse tangents for, or arc tangents for. So we will do tan inverse of 40/75, which we will go to the calculator for, and we will say that theta is approximately second tan 40 over 75. I've got 0.490 radians, but I might just I'll probably steal that number from my calculator rather than typing in 0.490. Okay. All righty. Okay, so let's take the derivative. I think we have everything we need here. If we find out we need something else, I mean, we need to be able to plug everything in except for one thing. So let's take a look at the formula we're going to actually take the derivative of. Tangent of theta equals A over B is static, so we'll say A 75ths. So let's take the derivative with respect to t of both sides, d dt of tangent theta equals d dt of A over 75. Okay. Usually don't write that step out, but I think it's kind of good to see what we're doing. So on the left, we have to take the derivative of tangent theta. What's the derivative of regular old tangent? Secant squared, yes. So the derivative is secant squared theta. We do, yeah. So, and that's going to be times d theta dt, which is what we're looking for, right? We want d theta dt. Didn't write that down here.
At this time, all students taking the Keystone exam, please transition to your testing room. And this is a reminder that no electronic devices, purses, or backpacks are allowed in the testing room. Please put those in the locker first. Thank you.
All righty. I actually think we can make this even easier in a minute. I did this a really hard way on the homework that I was working on this morning. We're doing it the easier way, and there's something even better here that we can do, I think, in a second. But what's the derivative of A over 75? Say that again. Negative 75? But it's not 75 over A. I think you're treating it like 75 over A instead of A over 75. By the way, I guess I shouldn't write it on the board if I'm recording for half the class. A over 75 is equal to 1/75 times A. The letter A makes it a little bit weird, but what if there was an X there? What would you tell me the derivative is? 1 over 75, yes, correct. So that A over 75 is just 1/75. But we do need the chain rule, so that's going to be dA dt. Righty. What did you say? Maybe. Oh, how the heck did you get that? You did quotient rule. I didn't catch quotient rule in your head. All right. Yeah, I mean, if you do the quotient rule on that, you will get 75 over 75 squared, which is also 1/75. I like it. Yeah, I wasn't listening for that, and I totally didn't hear it. All right, cool. So let's see. Do we know? We still have some things. ADT is still 3. So we've got 1/75th times 3. We've got d theta dt. Now, my instinct was to just go ahead and do the secant squared of that 0.490, but I realized we have the right triangle. So if we kind of jump back to this stuff, right? Remembering that our secants, our cosecants, and our cotangents are just the reversals of these things, right? So, but it's a little bit of a weird mashup. So sine goes with cosecant, so cosecant is HO. Cosine goes with secant, so secant is HA, and cotangent goes with tangent, which is A over O. So I actually can get the secant of theta not by relying on my calculator. So we actually didn't need this, didn't hit me until this is like I said, this is the third distinct way I've done this problem today. We can just rely on our calculator. So I can just do secant is H over A. I can take the hypotenuse over the adjacent, which would be 85 over 75. And I'm going to check myself. Well, so it's not the same number as what? It shouldn't be the same number. What it should be is if I do 1 over cosine of 0.490, I should get something really close to 85/75. 1 over cosine 0.490. That will tell me that I'm doing the right thing. And 85/75. Yeah. Yep. Yeah, they're good to about 4 decimal places. So yeah, so that absolutely works. So you can, rather than actually having to rely on the calculator to do the trig, I've got all A, B, and C there. I can figure out any trig function using SOHCAHTOA, or in this case, we needed secant squared. Okay, so in the end, let's clean this up and get ourselves an answer. We need d theta dt. So we have, on our left side, 3 over 75. Actually, wait, let me just write d theta dt equals. Yep, 3 over 75. And we need to multiply that by the reciprocal of the other side, which would be 75 squared over 85 squared. We'll get rid of one of those 75s, and we will have our answer. Morning. So it sure looks like I need to type 3 times 75 divided by 85 squared in my calculator, right? Yeah. Yes. Is that what? That's my coffee, yeah. Yep. Yes. Cool. All right, and that gives me 0.0311. We'll just need one of those ones. Okay. Ooh. If you kind of think about, you shouldn't get a very large answer there, especially because number one, we're in radians, so we've got small numbers to begin with. But as that balloon goes up, your angle can only increase by so much. It can't hit 90. So the higher and higher up the balloon goes, the smaller that's going to be. So that does. By me doing that with my hand, what I could do is I could pull up the Desmos that I made for it. Let's see, there it is. Example 7, there it is. Ah, yes. So there is our balloon. And that's our angle increasing. If I let that go up, like if I let this balloon go up to like 1,000, the highest amount that angle could ever be, it won't ever get there, but it's approaching 90. It's approaching 90, but it would have to be really, but it's not ever going to get there. So let's see, we were at 40 feet, right? You know, so this isn't accurate, but let's see how much, and it's raising 3 feet per second, right? All right, so let's take a look at our angle of elevation at 40 and then at 41. 40, it's 28.07. Let's see what it is at 41. 28.6. So that went up by about 6/10. But that was 3 seconds too, because it's going up 3 feet per second. Oh, backwards. All right. Yeah, not a good. I hadn't thought it through. If I thought it through, it. What's that? Sure. Woman smiling.
Woman smiling.
The balloon. Yeah, it wasn't much. Just a couple of lines. Just a couple of lines.
Each of the eye level.
Yeah, I made it so that it was. Yeah. Yep. All right. Let's take some time and get some work done. When I was working through some examples that you guys are going to work on today, this morning, looking at, yeah, is this one? Oh yeah, 17C. 17C is, you might want to put a star next to that one and leave that one go till the end. That's a tricky one. Or if you really want to get some help on it, we can do it that way too. But however it is, if you're at home and you get to 17C, I would leave that one for last.